Okay, welcome everyone. We just heard an excellent ITC colloquium, and I say excellent simply because it was about physics. Matias, we love physics. And Matias Zaldarriaga used to be a senior member of the ITC, that's why he speaks about physics. He left us, when was it, a decade ago? Yes, or,
it's a little bit more now.
How much is it?
Yeah, more like 16 years.
16 years. Yeah, you are welcome back anytime. He's now at the Institute for Advanced Study at Princeton and did the important work on the microwave background, and more recently is interested in gravitational waves, as he described. But we will hear from him about some additional work on gravitational waves in a few minutes. And then we'll hear from Christina Lindberg from Johns Hopkins. Is Christina here? Oh. Who will tell us about reading between the stars, resolving the multiscale interstellar medium in local group galaxies. And after that, we'll hear from Weicheng Zang from the CFA over there, who will tell us about an Earth-mass planet in a time of COVID-19. So there must be billions of them out there, but you are referring to one. And then we'll hear from Meg Davis at the University of Connecticut. Is Meg here? Meg? Over there. Who will tell us about identifying binary supermassive black holes with Rubin, which is very much related to what Matias was describing. So maybe we'll resolve the puzzle that he was showing with Rubin. That would be very interesting. Go ahead, Matias. Just make sure that you have a mic on you.
Which one is?
Yeah, that one.
Okay, great. Okay, so it's great to be back. And here I just want to give a little bit of an advertisement to other things that I've been doing with gravitational waves. So with a bunch of now former members, somehow we got into analyzing the LIGO Virgo data for searching for black holes by ourselves, mergers of black holes by ourselves. And the group grew a lot, and we are kind of the independent pipeline that does pretty much similar that LIGO does, but without different methods and different things. So I wanted to advertise a little bit that line of work. So we're always trying to look for things that LIGO is not doing in terms of either searching for things that they are not searching for, or methods differences. It turns out that there's lots of places that one can improve. And let me just highlight the latest thing that we've been doing, which is about searching for events for which there's also not just quadrupole radiation from the binary, but that the effects from octopole and higher harmonics emission is important. And the work was mainly done by these two guys. So just to quickly say the context as to why this might be interesting. So gravitational wave data is some sort of time series. We have templates that we cross-correlate and try to see if at any point in this time series there is something that looks like a gravitational wave. That's a sketch. The 2-2 means quadrupole radiation, but systems, especially, for example, if their mass ratio is not equal to 1, for example, produce a lot of L equals to 3 radiations. Also, if the merger is in the band of LIGO, that contribution is higher. And so if you can in your bank or in your templates include the effects of the higher harmonics, you might gain some additional signal to noise. So, and the reason people had not been doing that is because computationally it seemed very difficult to enumerate all the possible shapes of waveforms if you had to include all of these different multiples, because if the radiation is only quadruple, there are a lot of degeneracies between parameters. A lot of different systems end up having similar waveform, and you have to search for fewer things. But if you want to disentangle the higher harmonics, then more parameters start to matter, and it looked like computationally very difficult, but we managed to figure out a way to do it, and I'll tell you a little bit about the results for that. The other reason it's important is not just because you might have some additional signal to noise that might allow you to observe something that you wouldn't otherwise miss. The other thing is that very important in all of the gravitational wave searches, ours and LIGO, is that the detector produces a lot of things that are junk that might confuse you with gravitational waves. So a part of every pipeline is to find the best match waveform in some way or another, take it out from the data and see if there's anything left. And if there's anything left, you decide this is not a gravitational wave. But if there's a lot of 3-3 mode, there's something left. Or if the system is precessing, the 2-2 mode without precession, which is the real bank that everybody uses, the signal looks different, and so there will be a residual. And so, especially for heavy systems where the background is very big, we would be throwing them out. That's the reason to try to improve those searches. And this is just an example of the background in the searches. If everything was Gaussian noise as a function of how high a peak you would see in this match filtering, it would be some sort of power law in this kind of plot. But for heavy banks, you see this tremendous tail, which is all this junk in the detector, which we throw out by trying to demand that it looks like gravitational waves. But it's very dangerous in the sense that higher modes, precession, will put things into this is not a gravitational wave bucket. Okay, so that's the reason we're doing it. And we have done quite a few of those type of improvements, which resulted, for example, this is in O2. Our search, we claim, has much fewer background than the LIGO search. So, for example, this is some old data. This is signal to noise in one detector, signal to noise in some other detector. Dots are backgrounds in our search. LIGO background has a different distribution to the extent that this guy, for them, was something that they didn't know at the time whether it was real or not. But in our search, if you see the dark points, it's 2,000 simulation of 2,000 LIGO runs. It's impossible to get something like this. So it makes a big difference how you clean the data, blah, 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 because of these tremendous tails. So anyway, so these are examples of things in the data that are problems that if you manage to identify automatically and clean, you can reduce very much that tail of that distribution. And then you can, things that you might have lost, you found, or you can, so you will have a list of things that for LIGO were borderline or below their threshold that for you are more sensitive. And you would also change the significance for the borderline LIGO things. Some of them you would claim that they're very sure, that you're very sure that they're events, and for some of them not so much. And so the search for the higher modes resulted in 14, so I'm just here quoting the things that for LIGO were below their threshold, but for us were above the threshold. There were like 14 events. I mean, at the current time in gravitational wave astrophysics, there's like 100 events, and we're all trying to figure out, the outliers of all of the things, the very massive ones, the very spinning one. And for that, having these additional events, for example, there is some very heavy things. There's this tendency of things to be spinning aligned with the orbit. So, and finding things that are a little bit spinning quite a bit and so on. It's kind of interesting because we are still in the regime of small numbers. Of course, the things that we found that they didn't find are more borderline than the golden events that everybody found that they're very easy to find. So in this latest paper, we produced a catalog of new events, which with interesting properties, some very heavy ones, some mass ratios that are not equal to 1 as well. And we are now working on incorporating these events into the population analysis to see if they change or not the inferences of what the population is. And I leave you with two. This is from before including this event, so this is the current state of the art. Just two things that might to keep in mind when you see next type of papers that 04 events are going to come out from LIGO and a population. One is the spin, and there is some evidence. So these are histograms of the spin of the black hole, the component of the spin along the orbital angular momentum. Positive here means that there is a component of the spin aligned with the orbital angular momentum. Negative would be anti-aligned. And there's some hint that, for the most part, most of the events are not spinning, but there's some hint that if you see some spin, it is aligned with the orbit, and this might be some clue as to the origin of these binary black holes that are still in debate. But it's still a little bit of a borderline situation. There's some possibility that some are anti-spinning or not. That's where the debate is. So that's one place to look at, and having more events will help. And the other one is the fact that the distribution, the rate as a function of the mass of the black hole, say the primary mass of the black hole, seems to have some structure in it. And there seems to be heavy black holes that are above what one might think is this pair instability supernova type of threshold that sets a maximum mass for these black holes if they are first generation objects. There seems to be some peak around 30 solar masses. But all of this is still a little bit model dependent. There's not that many events. How you model things seems to matter. So finding heavier events and finding more of them will change, allow us to say a little bit more. So keep posted. We will have a paper with the results from our search on the old data, but more importantly, keep an eye on the soon-to-be released catalog from LIGO from the new observing run, which will have a big increase in the number of events. So I'll stop there.
Matias, obviously the LIGO experiment is remarkable in terms of pioneering a new frontier, but there is one disappointment. And that is that all the sources reported so far are things we know about. So when you do the analysis, did you see any? Because
we quickly claim to have known the existence of these very heavy black holes. Oh, I always said they were. Okay. But maybe not run-of-the-mill.
But my question to you is, do you see anything strange? Any source that does not match the kind of binary black holes or neutron star black hole systems?
In terms of, we've done searches, I didn't put, trying to find objects with strange tidal deformabilities that are not black holes. We couldn't find anything. So I think the quick answer is no. If you discount the fact that these black holes seem to be very heavy, there's nothing different. Another potential thing that would be very interesting would be to find, compact objects with smaller masses, which that would be some sort of, for example, primordial. But this would be it's very difficult, given that there are stellar mass black holes that you will read. That's the easier place to find new physics. But if we were to find, 0.5 solar mass binaries, that would be very compact black holes or something along these lines. That would be. And there seem not to be out there. People have searched. It's more difficult to search for those, but for the moment, we have
no physics so far.
No.
Okay. George,
Yeah.
go ahead.
So, Matias, you surely are aware of the fact that during the current 04 run of LBK, no neutron star mergers have been observed. No neutron star black hole mergers have been observed. They're
Yes.
all BBH.
Yes.
And what's gone wrong with LIGO?
Look, I don't think anything has gone wrong with LIGO. They got very lucky. We knew that the binary neutron star, they had gotten lucky because we could have seen, or they could have seen, that thing to much further distance. So that the distance of the binary neutron star, 170817, was close, right? So we knew they got lucky. Now they seem to be getting unlucky, or the rate, I mean, the rate estimate for the rate is going down. What can I say? Unfortunately, also, maybe this is not the best time for getting another binary neutron star because there's no Virgo, or Virgo is not working very well, so localization will not be very good. So maybe the universe is being nice to leave the binary neutron star to the time when the localizations are going to be better, and you will follow them up more cheaply, maybe.
Any other questions? Not, let's thank Matias again.
Is that making a bunch of noise? All right, can people hear me okay? Yeah. Awesome, okay. I am Christina Lindberg. I'm a graduate student at Johns Hopkins University working with members of the ISM STAR group at Space Telescope. And today I'm really excited to be here to present on resolving the multi-scale interstellar medium of local group galaxies. And I just want to take a second, right, to acknowledge that the interstellar medium of galaxies is not spherical blobs of gas with, homogeneous distributions, but in fact exhibit incredible multi-scale structure from kiloparsec scales all the way down to sub-parsec scales. And what ends up happening is that a lot of this multi-scale structure has a huge impact on where star formation occurs within galaxies, but also how feedback processes from, for example, AGN or massive stars imbue energy and momentum into their surroundings. And so galaxy evolution is really, in the grand scheme of things, a bunch of small-scale processes propagating up to kiloparsec levels. And so we need to find a way to study the ISM at these parsec scales if we want to properly model these galactic ecosystems. And not only do we want to just, not just study the ISM within, giant molecular cloud environments, but we want to study them across galactic environments and across metallicities if we actually want to model these systems across cosmic time. And so one of the ways we can study these is by looking at nearby galaxies within the local group. Here are some of my favorites. But in particular, right, what's really valuable about these galaxies is, in something like the Small Magellanic Cloud at 60 kiloparsecs away, we can point, HST or JWST at this galaxy and, resolve an incredible amount of substructure within these sorts of regions. And I want to emphasize that even 10 times further out in something like M31, the Andromeda Galaxy, at almost a megaparsec distance away, we can actually still resolve individual stars with high precision photometry, like with HST and JWST, and eventually Rubin. And so this means that if we can resolve the individual stars, we can characterize them. And if we can characterize stars, we can also probe how much extinction from dust is blocking the line of sight. And this gives us a very, very powerful diagnostic for tracing the ISM across a bunch of different gas phases. So we're not just constrained to looking at atomic emission or molecular emission, but we can go across these different phases. And so to just quickly recap how it is that we actually do this sort of analysis, we know that stars have some intrinsic underlying spectrum based off of their temperature and mass. But if there's any amount of extinction along the line of sight, this is going to block some amount of light from the star. And what we end up observing is an extinguished stellar spectrum. But one of the critical things that's important to note is that dust does not block light, uniformly across all wavelength ranges. It preferentially extinguishes shorter wavelengths, especially towards the ultraviolet. This is why JWST has been really paramount recently, because it's allowed us to see through the dust. But so if we get enough wavelength range of a star, or enough of a spectrum of a star, we can actually characterize and infer the amount of dust along the line of sight. So I do this analysis with something called the Bayesian extinction and stellar tool. And what's really critical for our analysis is that we don't actually need spectra to do this. If you just get enough photometric observations of a star across a variety of wavelength regimes, you can do the same sort of analysis with multiband photometry. And if you can do that, that means we can get extinction measurements for thousands of stars, if not millions of stars at once, rather than individual spectral analyses. And so this is what I've been working on for the last 5 years as a project called Scylla. It was a massive 500-orbit HST imaging program to survey a vast amount of galactic environments within the Magellanic Clouds. These are some of our closest dwarf galaxy companions. We think they're falling into us. Very kinematically interesting. They've been orbiting each other for a long time. And we think they might have interacted 100 million years ago. And so there's a lot of interest in kinematic structure, but even more importantly, they're very low metallicity. The LMC is roughly half solar metallicity, and the SMC, or the LMC is half solar metallicity, and the SMC is roughly a fifth. And so they provide this really interesting environment to study a lot of these ISM structures happening at parsec scales. And so, for example, here's a three-color image of one of our fields that we got. This is near the 30 Doradus region for people who know about that. And when we actually do PSF fitting and characterize the stars in this field, we see something like this. And you might think that's a lot of non-reddened stars with 0 magnitudes of extinction. But there's also some stars on the back or some stars on the left-hand side that look like they have quite a few magnitudes of extinction applied to them. And the one thing we have to really consider when we're doing this sort of analysis is the fact that when we're looking at external galaxies, there's going to be foreground stars in front of the majority of the star-forming material, as well as behind. And so if we actually remove these foreground stars, we start to see a very different, more coherent image of what's actually going on with the interstellar medium. So these are the exact same sources, just actually WCS file corrected. And so we can use these sources as probes for the underlying structure of the interstellar medium and interpolate between them using something like 2D Gaussian processes. And this gives us a really high-resolution understanding of what the dust structure is doing within these fields. And just to convince you that we're not totally crazy in doing this, we can compare this with something like existing infrared emission surveys that target the same exact field. And you can see there's incredible morphological agreement between these two seem completely independent measurements of the dust. And so that's if we have both of these measurements, we can start to look at how the emissivity of the dust changes as a function of the metallicity. We can also look at ancillary ISM tracers. This field just happens to have CO data. I would like to point out very, very few fields have this high resolution ALMA observations, but we got very lucky, and this is why it's the example field we use. But essentially, you can see that there's incredible amounts of CO structure, and the extinction maps are capturing a lot of it. Now, why is there no, a lack of extinction up in the upper right-hand corner? We don't know yet. That is an active point of investigation. But it means that we can essentially use these, we can make extinction maps for any galaxy that has resolved stars and multiband photometry. And this will enable a huge amount of science, like I said before, looking at dust emissivity. This is really useful, especially for higher resolution or for higher redshift studies that use that as a tracer of the ISM. We can also, as I mentioned previously, look at the distribution of different gas phases and calibrate those relations as a function of metallicity, potentially even constrain the fraction of molecular gas that is not being traced by CO. And lastly, one of the things I'm really interested in is looking at where massive stars within these fields are located and trying to figure out how are these stars changing the morphology of the ISM around them before they even produce a supernova. And so I just want to emphasize again that there's been a huge effort in the last 5 years to ensure that we have UV and optical coverage with HST of many of these local group galaxies. There's a local ultraviolet and infrared treasury program, paper is coming out soon, that got really high-resolution HST coverage of a lot of these galaxies. And there's even more to come. So I'm the PI of a project that's going to look at a really interesting star-forming region, and it's this tidally disturbed wing of the Small Magellanic Cloud leading towards the LMC. Why is there a star-forming region in such a kinematically, disrupted region? We're not sure. We want to find out. And there was recently just confirmed in HST cycle 32, we're going to get more panchromatic coverage of 4 additional dwarf galaxies within the local group that have existing VLA H1 coverage. And so I'll leave it off here and say, I'm very excited for all the dust mass we can create in these galaxies. And I'll take any questions. Thank you.
There must be some contribution from our own galaxy when we look out. So how do you separate small-scale structure in our galaxy from the distant ones?
Right. So the SED fitting technique just characterizes everything. We're definitely not doing the differential extinction like some dust mapping techniques use, like in the M31 have done in the past. The main, idea is a lot of these galaxies are not located near the plane of the galaxy, and so if there is any contributions from Milky Way foreground, it tends to be very small. In the SMC and LMC, the foreground extinction estimates are like 0.1-ish magnitudes, and so when we're characterizing some anywhere between 1.5 to 3 magnitudes, the 1.5 is a trivial contribution to that. And in addition, a lot of the answer, if we are looking at far infrared emission, that's also going to have Milky Way contributions. So it gives a better apples-to-apples comparison.
Thank you. Yes, please.
When you refer to metallicities of LMC and SMC as one half and 1/5 of the solar, that's actually the mean stellar metallicity.
Sorry, what?
That's the mean stellar metallicity.
Mm.
It's not the metallicity at the current epoch, where you see the ISM because of the self-enrichment. I'm saying this because we measured spectroscopic metallicities for star clusters in the LMC, and they go as high as -0.2 dex. So how are you taking this into account? Because there might be metallicity variations across the disk as a result of local efficiency or inefficiency in self-enrichment.
That's a great point. So as part of our SED fitting process, we do also characterize the metallicity of the stars in addition to the extinction as just part of the fitting process. So we could use those as probes. But yeah, obviously relying on ancillary metallicity measurements is going to be critical for confirming the metallicity measurements that we get and sort of tracking that variation. But yeah, that's a good point.
So for the parts of the map where there is CO emission but not as much extinction, so even within the galaxy there is this thing of foreground versus the stars are in front or behind that cloud. So is there any information from the radial velocity of the CO, whether it's behind or in front of the stars that you can see?
Yeah, so that's actually, so this field we've been, as part of our fitting methodology for the SEDs, we also get distances, and so we've been trying to, this is active work, so I can't, quote anything, but we do, find slightly separate distance measurements to these different CO structures, and there have different radial velocities too, based on the CO. And so this is like a paper we want to write as soon as possible once we have time to breathe and do that. But no, for sure, the radial velocity and especially H1 velocity measurements will be critical for especially deconstructing some of the more star-forming shells that we have. This was actually one of the things we were proposing to do in the wing region. We have ALMA CO observations, we have ionized gas observations, we have H1 observations as well, and so we could do almost like a full 6-dimensional kinematic deconstruction of this region if we can get our SED distance techniques good enough for that.
Last question, Tony.
Oh, so I'm wondering, is the Euclid data set going to allow you to do this on all galaxies?
Ooh, I think so. Or any galaxy with resolved, where we can resolve the stars. This was actually a point of discussion we had a couple months ago was, yes, whether Euclid would be usable for this sort of analysis. And I think as long as you have multi-band data, you don't actually need the UV coverage. That's mostly useful for constraining what the extinctive properties of the dust, i.e., what's the total to selective extinction. But right, in theory, if you just have enough multi-band coverage, like if you have enough bands of coverage, you could still do the same analysis. And so I think we applied for something, or we're in the works of applying, drafting something to work with Euclid data, but that's still very much not up and running yet. But yes, in theory.
Excellent. Thank you so much, Christina.
Hello? Okay, thanks very much. My name is Weicheng Zang, a CFA fellow who joined CFA 2 years ago today. Now I'm going to introduce a story about an Earth mass planet in the time of COVID-19. Actually, this is the title of my paper published 3 years ago, and this title had two meanings. First, when I took observation in 2020, our Earth mass planet is in the COVID-19 pandemic. And the second, even with such a difficult situation, I still detected an Earth mass exoplanet. The low event rate and the short duration with a microline planet signal means that detecting microline planets requires high cadence wide field survey towards the Galilee bulge in order to have the capability of both finding a microline event and detecting the planet signal. But in 2020, many sites around the world were closed due to the pandemic, and it was hard to keep this ideal mode. But the crisis is also an opportunity. 32 years ago, Andy Gold and our genius Avi proposed a two-step strategy for such a situation. And even 1 year before the first microline event discovered by our former CFA director, Charles Alcock. And in the first step, a wide field survey with a low cadence aims to find a large number of microline events. And in the second step, interesting events found by the first step would be modified by high cadence follow-up observation from a global follow-up network to capture the planet signal. On the night of July 7th, I waited until 2 a.m. for the latest survey data because there are no data from survey for the past 5 days due to the pandemic and the bad weather. Then I found this event would peak at high magnification with 3 days and began my follow-up observation using the LCO Global Telescope Network and a telescope from an amateur volunteer in Brazil. 1 day later, based on my follow-up data, this event had deviated from the single lens model, the dashed line, and may have a planet. So I sent an alert email to the microlensing community for follow-up on a larger scale, but no response. Half a day later, with more data, I sent another alert, no response. Another alert was sent another half a day later, but still no response. But this event would peak at thousands of magnification within 10 hours. Finally, I sent an email to the leaders of the MOI group, which has one telescope in New Zealand, and I emphasize that the MOI data are unique because of the bad weather in Australia. Luckily, the MOI group trusted the young PhD student and observed this event 60 times that night. The blue line shows a binary lens model. The MOI data of the peak, these red points, are inconsistent with the binary lens model. And finally, we found the lens system has 3 bodies, and the complete coverage for the anomaly from our follow-up observation measured the microlensing parallax effect, and that's the lens mass and the distance, showing an Earth mass planet and a brown dwarf orbiting a star with half mass. With the mass and distance, we can predict the lens luminosity for a mean sequence lens. Based on the seeing limit image, the predicted flux for the lens seems to be brighter than the blended light to the source. In this figure, the two white lines indicate the source position. And the blended light seems to have an astrometric shift with the source, and is likely not the lens. However, extraordinary claims requires extraordinary evidence. I only indicated the other possibility in a footnote of my paper. Or the host could conceivably be a white dwarf. To confirm my guess, I need a high-resolution image from adaptive optics to resolve the blend. However, I was a PhD student in China at that time and cannot access any large telescope. I tried to assess the AO observation from the community, but they didn't believe the host could be a white dwarf, even though they only needed to submit my proposal to NOAA lab or NASA CAC. Finally, my friend, Zhang, who is a PhD student at Berkeley and studying AI in astronomy, trusted me, and we got a half CAC night from Berkeley. But unluckily, the CAC AO was broken for the first 2 hours for our CAC night. When the AO was back, we still couldn't observe our target because a supernova the supernova in a nearby galaxy happened 5 days before. For the Berkeley CAC time, a PhD student cannot be the PI, and the PI is a faculty member. The PI thought it was a low possibility that we can detect an Earth mass planet orbiting a white dwarf, so used the CAC to observe this famous supernova. Finally, thanks to Kermin's persistence, 7 minutes before our target was unavailable, we got the AO imaging. The AO image has an order magnitude higher resolution than the ground-based seeing limit image, and clearly shows that the blind light in the seeing limit image was from several ambient stars. The total flux at the event position is consistent with the source flux, and there is no detection of the lens flux. The host star must be a white dwarf. This is the first discovery of a small planet orbiting a white dwarf. This figure shows the planet mass versus planet host separation for all confirmed white dwarf planets. Before our discovery, there were only 5 giant planets orbiting white dwarf. The white dwarf planets around 1 to 10 AU are interesting because they may imply the fate of our Earth, and are during and after the AGB phase. And microlensing is the only method that can detect such planets in the entire planet mass region. And we can see 2 microlensing planets in this region. And these 2 planets make the frequency of white dwarf planets interesting. The microlensing detection for white dwarf planets require a measurement of the lens mass and distance. And so we can predict the lens flux for the hypothetical mean sequence star, and a non-detection of such flux would suggest a white dwarf. However, less than 10% of the microlensing planets can have the mass determination from the ground-based light curves. And also, the lens system must be close to our solar system, so the axis flux on the source star is detectable. Finally, only 10% of the microlensing lenses are white dwarf. So assuming the occurrence rate of white dwarf planets is the same as that of main sequence stars, at the current stage, at least 500 microlensing planets can only have 1 white dwarf planet detected. But now, with CAC AO observation for a few targets from the about 200 microlensing planets, we already discovered 2. So microlensing white dwarf planets could be very, very common. I have been leading a large project to systematically observe the microlensing planets using CAC, HST, and Gemini to estimate the frequency of white dwarf planets. And then, after the launch of the Earth 2.0 space-based microlensing telescope, and that I'm leading, more lens masses will be measured by the parallax observation from this satellite and the ground-based telescope.
and more sensitive high-resolution imaging will be provided by the Roman Space Telescope and the future 30-meter class telescope. We will revolutionize the field of white dwarf planets by a sample of about 30 white dwarf planets, and first determine the mass function of white dwarf planets. And finally, I want to end my story with Nelson Mandela's words: "It always seems impossible before until it's done." And thank you very much.
Weicheng, many of us lose sleep because in 7.6 billion years the sun may engulf the Earth and the Earth will fall into the center. And the sun will eventually become a white dwarf. So my question to you is, do we have hope? Because based on the fact that this planet survived the giant phase, how, at its orbital separation, so does it mean that as the sun loses mass, perhaps the Earth would move out a bit and therefore survive? Or can you say something about that?
Yes, Avi. Actually, I don't like to connect my detection with the future of Earth very much for several reasons. First, the micro detection only measures the projectile separation between the planet and the whole star. And the current projectile separation is 2 AU, so it might be a 10 AU or 5 AU planet. And then during the AGP phase, our sun will lose mass, and maybe our Earth will go outside. But I think the tidal interaction between the whole star and the planet may make the orbit of our Earth shrink. So I think this is a very blunt, a very new field, and need a lot of study. And also, I saw your blog. And I know you have a lot of idea about this system. So I would suggest the audience to read Arvi's blog about his idea.
Thank you. Any questions, comments? Looks like you explained perfectly well everything, so congratulations for the discovery.
Thank you very much.
Sorry, give me 1 second. Cool. Can you hear me? All right, awesome. Thank you for having me. Hi, my name is Meg Davis. I'm a PhD candidate at the University of Connecticut, where I work with John Trump, no relation, his joke, not mine, as well as these wonderful collaborators, multi-wavelength, multi-messenger collaborators. Today I'm going to chat with you all about some of my PhD work, not all of my PhD work. If you want to hear about the rest of my PhD work, you should ask me in the question portion. But today I'm actually going to chat with you about identifying binary supermassive black holes with Rubin, and if we even have a chance. Okay. I'm going to be a little bit reductive with the background, so please do forgive me. There are subfields of information that I have to cover in like 2 minutes. They're not going to get the time they deserve. But what you need to know is that binary supermassive black holes form through galaxy mergers. We expect that most galaxies in our universe have a nucleus, and that nucleus being a supermassive black hole. And so through mergers, they can end up in binary pairs. Over here on the left, I have real SDSS images of dual AGN, or dual nuclei, where they're kiloparsec to parsec scale separations. They're not gravitationally bound to each other just yet. Through interactions with gas, dust, stars, they lose angular momentum, sink into each other's gravitational potential wells, and end up in a binary pair. on like parsec to sub-parsec scales. And in this beautiful simulation from Duffel et al. 2020, we see that each black hole can actually end up with its own mini accretion disk, streams onto those mini accretion disks from a massive circumbinary accretion disk. That'll be important for later. I wish I had more time to go through that with you, but alas. So we know that these objects theoretically exist, and understanding or finding them will improve our understanding of gravitational wave astrophysics. These binary supermassive black holes are expected to constitute the gravitational wave background in our universe. They are very elusive gravitational wave sirens. They'll also further our understanding of galaxy evolution, hierarchical structure formation. We'll understand merger rates, extreme accretion environments, black hole seeding, etc. The issue is that we have hundreds, if not thousands, of candidates of these objects, but no full confirmation. Okay? And I'm going to tell you why. And also explain that this is for optical photometric searches. My cup of tea. You may have a differing opinion if you work in a different wavelength, and that's okay. But this is my work. So we, when looking for these objects, we're searching for a periodic signal. And binary supermassive black holes can produce a periodic signal through Doppler boosting, especially if these black holes are moving at some significant fraction of the speed of light through movement and through that velocity. They can modulate the light curve and produce a sustained sine wave of sorts. There's an asterisk up there because there are 1,000,001 ways in astronomy to make a periodic signal. This is just an example, a very simplified example. So when we're looking through light curves, we're looking for sine waves, pretty much. And we astronomers are pretty good at finding sine waves, even where there aren't any. But I'll digress. This is a real light curve of a candidate object, PG1302, one of our favorites, for example. So that's what we're looking for. What's the issue? Can we find it? Have we found them yet? Kind of. The issue mostly lies in the fact that single single quasars, so actively accreting very luminous supermassive black holes, exhibit periodic variability or quasi-periodic variability. And that is from fluctuations in the accretion disk, thermal fluctuations in their accretion disks. There are many models that you can use to model that variability, and most of them include a damping parameter. That damping parameter can cause periodic looking behavior. So single quasars can look periodic, and we're looking for periodic signals. This causes issues. And because the binary supermassive black holes are embedded in that circumbinary accretion disk, and if the variability comes from thermal fluctuations in that accretion disk, that means that those binary signals are also embedded within quasar variability too. To me, that's noise. To others, that's a signal. So we're looking for signals embedded with noise. Embedded in noise, it's also periodic. It's a mess, pretty much. It's your takeaway. Is there hope? There's always hope. Hope comes in the form, of course, comes in the form of massive time domain surveys, including Rubin. Rubin is expected to come online in 2025. First photon, I believe, is in March of 2025, which is very exciting. It may be one of our best chances at finding binary supermassive black holes. We've got a lot of massive time domain surveys currently running and upcoming. So it's a good chance. But not the only chance. Rubin's cadence baseline and expected number densities of AGN or binaries or of active supermassive black holes, 20 to 100 million. There's a good chance we're going to find that needle in Rubin's haystack. Okay. Rubin's also going to produce 20 terabytes of data every night. So this is a computational challenge. Very big computational challenge. So what did I do? And what questions are we looking to solve? Oops, spoiler alert. So we wanted to prepare for Rubin. And to do that, we were going to need to synthesize data, make millions of synthetic light curves. And then we wanted to figure out whether or not we could actually separate binary from single supermassive black holes. So triage single quasars. And then determine whether or not there are any types of quasars that cause problems. And there are. So with most things in life, you fake it till you make it. We had to fake data till Rubin comes online. And I wish I had a couple hours to walk you through how I synthesized light curves, because they're beautiful. I spent a lot of time making these, but we're gonna have to go fast. So I picked a variability model. I picked some sort of periodic signal, sine waves, added them together, and then simulated Rubin noise and observation, cadences, properties, etc. Okay. Again, I wish I had more time, but alas. And like I said, we're expected to observe 20 to 100 million supermassive black holes. And it's a numbers game, so I simulated millions of light curves. That was the first paper of my PhD. We chose 5 years just for the first 5 years of Rubin, which is expected to run for 10 years. Broad ranges of quasar and binary properties, quasar properties being mass, redshift, luminosity, and binary properties being those properties of the binary signals, amplitude, phase, period, signal type. Maybe it gets a little sawtoothy, for example. And I simulated both single and binary supermassive black hole systems. Then we wanted to try and throw detection methods at them. We're really good at fitting sine waves, like I said, to things that maybe we shouldn't be fitting sine waves to. And that's one of the easiest things to implement, especially when you're working with millions of light curves. It's a good place to get started. You've already seen this image, but we decided to throw some very simple sinusoidal curve fits at the problem and see what happened. Just see what sticks. In the top, we have a single isolated quasar in the binary. On the bottom, we have a binary. If you close one eye, maybe squint a little bit at the top panel, yeah, that's maybe a long period. It could be a little periodic looking. On the bottom, yeah, that looks very periodic. They're good fits. And that's what we did on all of those light curves. And through some simple parallelization, I can fit almost 10,000 light curves a minute. This is a computational challenge. We need computationally inexpensive detection methods to triage, get general trends, do some predictive work. One of my collaborators, Caitlin Witt, who's a postdoc, I believe is here at Northwestern, did some beautiful Bayesian fits, similar curve fits with a Bayesian spin. It took 15 minutes per light curve, and we actually found the same trends. So it's a numbers game. But y'all should check that out if you ever have time or are interested. So how did they perform? What could we do? It turns out, period and phase, we can recover them with a sine fit. I don't recommend using a sine fit for reasons that will be explained in the next slide, but you can do it. In this plot, we have parameter recovery, where the parameters are in the legend there, and defined for what parameter recovery means down here at the bottom. You'll notice very peaky, which is great. Amplitude, not as good. But high false positive rates, general definition, good chi-squared fit, that we could have a good period represented within the light curve itself. 60% for high luminosity quasars. I'm out of time, so I'm going to stop and move on, but I do have a summary slide for you, at least. We simulated millions of Rubin light curves, tried to fit them with simple signs, and it works, kind of, at least for phase and period. If you want to ask, I have at least 3 more interesting detection methods that I've applied to the data, but those are my extra slides. And we're really excited about Rubin. There is a chance, and there is hope, and also excited about Rubin. So, thanks.
Beautiful work. The Doppler boost depends on the spectral slope, right? In terms of the flux. So that's one way of verifying, because if you have a flare, it could be a change in temperature, but with the Doppler boost, you can see it. So are you using that in different bands?
Yes. Eventually, yes. So yes, it does The Doppler boost properties do correlate with what waveband you're looking in, what wavelength you're dealing with. But compared to quasar variability, they actually scale differently, even though they're correlated similarly. So there's hope that when you maybe turn to the frequency domain, we can separate them, which is exciting. You can actually see that a little bit in the standard periodograms as well. Per waveband in the bluer, where that line is, that's like the binary period I injected in these light curves. You can actually see that we've maybe detected it in the power. So can you see this? Yeah, right here. In the power spectrum, that we've verified that the binary signal is there. But when you look in the redder, you actually see you have other peaks that dominate the power spectrum, and that's from the red noise. That's from the quasar variability. It's causing confusion and issues in the periodograms, but if you turn to multiband and use all of that color information, works out.
Given what we heard from Matias, if there is a single source that PTA detects, you might identify which source it is. That would be exciting.
Oh, very. Or, and I highly doubt this, if we happen to find the electromagnetic counterpart first, it helps to localize in PTA searches. I highly doubt that's going to happen that way, but it'd be cool. Yeah.
Comments? Yes?
Yeah, so it's one of these typical arguments against the sinusoidal variability. In this OG 287, the favorite source, people claim that it might be explained by precession of a jet.
Mm-hmm.
So can you separate it with your methods, like maybe using something similar to what you're showing right now, the jet precession use variability from Doppler boosting?
Yes, I do believe that could be possible. In my work with these light curves as they stand right now, not possible. It's not simulated and not accounted for. But that's excellent future work, probably not for me, but for an undergrad, a grad, etc. Yeah, absolutely. There's also some interesting arguments for trying to even separate and account for the mini accretion disks. Perhaps there's extra emission, and then from the cavity that they carve out, missing emission as well, that could be modeled. Lots of dynamics at play that could be accounted for.
Since Rubin will be active for a decade, you can have a student yourself. You can become the faculty.
Yes. And I didn't get to it, of course, but I actually model up to 20 years as well. And that improves recovery rates, reduces false positive rates, et cetera, et cetera. Longer we go baseline, better chances we have. So we're going to have to wait a while, even though data is going to be coming in, to even start looking for these things. So lots of work to be done.
Excellent. Let's thank Meg again.